Welcome back to Physics 104B. This is the beginning of Chapter 27 on electromagnetic induction. In this video, we'll cover the first two sections. Section 27.1, Induced Currents. So far in our study of electromagnetism, what we've seen is that electric current produces a magnetic field. We've also seen that a magnetic field exerts a force on moving electric charges, and that includes a current. But the big question in physics in 1820s was, can a magnetic field produce an electric current? In 1831, two scientists, the English scientist Michael Faraday, for whom the unit, the farad, is named, and the American scientist Joseph Henry, independently found that electric currents arose in circuits that were subjected to changing magnetic fields. So the answer is yes, a magnetic field can produce an electric current. Here are some different experiments that can be done. You look on the picture on the left. If you have a conducting loop and there's an ammeter hooked up to it, and you just hold a magnet there, so keep in mind there is then a magnetic field in the presence of this loop. You can see the ammeter is reading 0. However, if you move the magnet through the coil or near the coil, towards or away from it, it produces a current in the coil. And this is what's called an induced current. Now, what they then found is if you move the magnet faster towards the loop, increasing the magnetic field in the loop even more, then there's going to be more of a current. And if you move the magnet in the other way, away from the loop, you're going to get a current, but it's going to be in the opposite direction. So these pictures show a stationary wire loop and a moving magnet, and moving the coil with a stationary magnet will have the same effect if we keep the magnet still and move the coil back and forth. So this is a very neat result that they got in 1831. The idea is that we can get a current with no battery, no source of electromotive force, except for just that there is a magnet moving relative to the loop. At the top of your screen are the 4 pictures that I previously showed for that experiment. Now look at the bottom where my marker is. Here we have 2 circuits, 2 closed loops. The one on the left has a battery, and the one on the right just has a loop with an ammeter, just like in the previous pictures. And notice they are not touching each other in any way. Now remember from the previous chapter that a current, I'm looking at the one on the left here, an electric current produces, it has a magnetic field to it. So essentially this loop on the left, the current is powered by a battery. Effectively, it is a magnet, just like the bar magnets in the previous pictures. So if we move it towards or away from the circuit on the right, it will induce a current on the right. So a current is also induced when the current in an adjacent circuit changes and there's no motion required, meaning instead of moving the circuit on the left, we can just have a little switch there. When we open the switch, it shuts off the current on the left. That gets rid of the magnetic field, and so it'll change the current. We close the switch, it turns on the current on the left, that produces a magnetic field, and that production of the magnetic field will change the current on the right. So this is the idea of electromagnetic induction. Electrical effects arise from a changing magnetic field. It's not the presence of a magnet itself. Remember the original picture that I drew. When a magnet is just sitting still, not moving, then there's no effect, there's no induced current. But a changing magnetic field will induce a current. This brings us to section 2, Faraday's law. With an induced current, there is no battery, but there still needs to be an EMF, an electromotive force. And so we call this an induced electromotive force. I want to introduce to you the concept of magnetic flux. In general, when we talk about flux in physics, flux is vectors of something that are passing through a surface area. Now, I want you to think, because this is useful for understanding concepts in induced currents, think about raindrops on a surface. Maybe this is a important paper you're bringing into your classes and it's raining down. We don't want it to get wet. And so we think, what are different ways that we can reduce the raindrop flux onto our surface? So right now we're holding it out nice and flat, horizontal, so that all the raindrops will hit it. Well, three different ways we can think about to reduce the flux of raindrops on our paper. One is for the rain to stop. Well, there's not much we can do about that, but that is one way to reduce the flux, is to have fewer raindrops. Another way is to tilt the paper, to tilt the surface, so that while there's still the same amount of rain, and by the way, in this analogy, the raindrops are the magnetic field going through a current loop. So while there's still the same amount of raindrops, fewer of them will hit our page. And a third way is to reduce, to have a smaller surface. So maybe to fold our paper up in half and quarter, less rain is going to hit it. Well, this analogy works for when we think about how to reduce or maybe to increase, depending on which way you want to go, the amount of magnetic flux through a current, through a loop rather. Think of this as a loop of wire. So one way is just to, on the left, we can change the magnetic field. Another way is to tilt our loop. And another way is to have a smaller or larger loop. So now let's think about the flux in a uniform magnetic field, particularly the flux of the magnetic field lines. We'll call that the magnetic flux that is going through a conducting coil, a conducting closed loop. You can see my picture here. Here's the magnetic field, and we'll start just by treating this the mathematically easiest way. Just think of it as a uniform magnetic field. And there's our loop, and I've shaded in the face of it. And notice I've drawn a vector that's perpendicular to the face of it, and the angle between that vector and the magnetic field lines will give it the angle theta. The flux of magnetic field lines, we'll call it the magnetic flux. Here it's the Greek letter phi with a subscript b for magnetic field, is equal to the component of the magnetic field that's perpendicular to the loop times the surface area of the loop. So that describes essentially how much of the magnetic field is going through the loop. Now that becomes the magnetic field times the area times the cosine of that angle theta. Look down at the picture to the middle and to the left. When the face of the loop is parallel to the magnetic field, I want you to see that that angle is 90 degrees, and the cosine of 90 degrees is 0. So in our equation, the magnetic flux becomes 0. And here you can visualize and you can see that the magnetic field is completely, none of it is going through the loop. The picture at the bottom on the right, here the flux is maximized. So here that's a 0 degree angle. So the magnetic flux is the magnetic field times the area. And you can see cosine of 0 degrees, of course, is 1. So the flux is B times A. Here it is at the top, the magnetic flux through a conducting loop is B times A times the cosine theta. And the unit of magnetic flux is the Weber, and the abbreviation for that is capital W and a lowercase b. They couldn't just use capital W because that's already reserved for watts, so the Weber is WB. Now you can look at the equation at the top and see that the units of a Weber, dimensionally it should be Tesla times meter squared, and that's what it is. Now, when we get into a changing magnetic field for a non-uniform field, this is the more general equation here, that magnetic flux is the integral of the dot product of B and dA. But for a uniform magnetic field, that reduces to just the dot product of BA, which of course is BA times cosine theta. Let's look at example 27.1. The magnetic flux with a solenoid. It says a solenoid of circular cross-section has radius r. It consists of n turns per unit length and carries a current I. Find the magnetic flux through each turn of the solenoid. So you can see what a solenoid is, just a tightly coiled metal with a current that's going through it. And the magnetic field on the inside of the solenoid This was actually solved in chapter 26 in a section that I did not cover in the video. But the magnetic field in a solenoid is the permeability constant times n, which again, it's describing n as not just the number of turns, but the number of turns per unit length times the current. You can see my picture on the left. There's my zoomed out picture of a coil, and we talked about that in a previous chapter. And then just zooming into the inside, here's what it looks like. And there's the equation at the top. We want to find the magnetic flux through each turn of the solenoid. So as we consider a turn of the solenoid, now we're looking straight into the solenoid. There's the current and the magnetic field on the inside. As I've drawn it, we use the right-hand rule. We're going to take our right hand and curl our fingers in the direction of the current, and our thumb points into the page, so it goes into the page there. The magnetic flux is BA times cosine theta. So B, given at the top of the page, is mu naught times Ni, times the area, which is pi r squared. And you can see the cosine of the angle in this case is just going to be 1. This is where it's maximized when the magnetic field lines cut straight through the loop, as it is in this picture. So we put those all together and we get that the magnetic flux is mu naught times n times the current times pi r squared. Let's look at example 27.2 with a non-uniform field. It says a long straight wire carries a current I. A rectangular wire loop of dimensions L by W lies in a plane containing the wire, with its closest edge a distance A from the wire and its dimension L parallel to the wire. Find the magnetic flux through the loop. Well, let's look at the picture. I've drawn it as it's described. There's our current going through the wire. I've made the current go up. There's I. And we think about what I've drawn in purple here. The magnetic field, to see what direction the magnetic field is going, you grab the wire with your right hand. Your thumb points in the direction of current. And notice the direction as I've drawn it that the magnetic field goes around it in a circle. That's the direction your fingers curl. So everything to the right of this wire is the magnetic field. It goes in. I've written this equation. We found this in an earlier chapter, that when you have a wire with the circular magnetic field coming from it, the magnetic field is mu naught times the current divided by 2 pi, and that r is the distance from the wire. And here's the loop, and notice what I've drawn in purple, that closer to the wire the magnetic field is strong, farther from the wire it's weak, so that's the nature of the non-uniform magnetic field. We're going to use this equation where my marker is, that phi, the magnetic flux, is the integral of B dot dA. So it's the sum of that cross product, the magnetic field through the entire area. What we need to do is divide the loop, current loop, into rectangular strips, and they're going to be of length L and width dr. So you see that purple rectangle that I've drawn in there. So the area of every one of these rectangular strips is L times dr. All right, let's go down to the equation. Magnetic flux is the integral of B dA, and that becomes B times dA times the cosine of theta, but in this case, theta is 0 degrees, cosine of theta just becomes 1. So we're taking the integral of B dA. Now, we're going to change dA. Remember up here, dA, the area of each rectangle is L dr. So let's turn that into L dr, and here we have B is mu naught I over 2 pi r. So we have all those things in the integral. And notice I've put in the limits of integration. The low end limit is A, because that's the distance from the wire. The high end is going to be A plus W over here. Let's now factor out all of the constants to the left of the integral. So that's going to be mu naught IL over 2 pi. What we're left with in the integral is just 1 over r dr. So that becomes mu naught IL over 2 pi, and the integral of 1 over r dr is natural log of r. And when we take it with the limits of integration, we get the magnetic flux is mu naught IL over 2 pi times the natural log of A plus W over A. Well, now that we've developed the concept of magnetic flux, we can now state Faraday's law of induction, which says that the induced electromotive force in a circuit is proportional to the rate of change of magnetic flux through any surface bound by that circuit. Here's the equation right here. We'll use this script E for the electromotive force. There's a negative sign and then the rate of change of magnetic flux, so negative d phi over dt. The idea of the negative sign is that the induced EMF opposes the change in flux. So whether we increase the magnetic field, we decrease the magnetic field, maybe we're increasing or decreasing the size, whatever we're doing to change the magnetic flux, the current is going to be induced that will oppose that change in flux. And we'll talk more about that in the next section. So with that in mind, let's do the next example. This is example 27.3. Induced current, a changing magnetic field. The example says a wire loop of radius 10 centimeters has resistance of 2 ohms. The plane of the loop is perpendicular to a uniform magnetic field B that's increasing at a rate of 0.10 Teslas per second. Find the magnitude of the induced current in the loop. You can see my picture right there. We have the radius, the resistance, which will help us find the current, and this is the part that's going to lead us to the EMF. It's the rate of change of the magnetic field. You see what I've done here with the equation. I've changed Faraday's law just a little bit. I'm getting rid of the negative sign. And for our purposes in this class, it's going to be useful to just ditch the negative sign and think of this in terms of the magnitude. So when you see me write out this equation, when I work it in different examples and in the homework solutions, I will always get rid of the negative sign and just treat this as a magnitude. With that in mind, let's do this. We have the rate of change of phi, which is the rate of change of B times A. And again, cosine theta, that's not changing. That's just 1, so that's moved out to the side. And it becomes the rate of change of BA. Anything that is not changing in this derivative, factor it out to the side. So in this case, area is not changing, and we're left with area times the rate of change of magnetic field. So area is pi r squared times dB dt, and we're already given all those values. When we calculate them, we get the electromotive force is 3.14 millivolts. The question is asking what is the current, the induced current. By Ohm's law, current is the electromotive force divided by resistance. And so 3.14 millivolts divided by 2 ohms is 1.6 milliamperes. I want you to notice we don't actually care what the flux is at any given moment. We don't care about solving for flux. All we care about is finding its rate of change. Let's do another example in the book, example 27.4, this time of a changing area. It says 2 parallel conducting rails, a distance L apart, are connected at one end by a resistance R. You can see my picture there at the top. A conducting bar completes the circuit, joining the 2 rails electrically, but free to slide along them. The whole circuit is perpendicular to a uniform magnetic field as shown in the figure. Find the current when the bar is pulled to the right with constant speed V. All right, so we're going to grab this bar and slide it to the right. And the concept that's being shown here is something called motional EMF, where a current is actually going to be induced from motion, from mechanical energy. We use the equation that the induced electromotive force is d phi dt, and once again we replace phi with BA. In this case, the magnetic field is not changing, so it gets factored out to the left, and we're left with B times dA dt. Now the area, we're referring to the area of the loop that's in the current. And so it's what I'm tracing out with my marker right here. So it's going to be the rate of change of this rectangle that is L in height, and in width it is X. And so once again with this derivative we're going to factor out anything that doesn't change. L is not changing, so L goes out to the left, and we're left with BL times dx dt. Well, dx dt, how much the width of this, in the horizontal direction, that is the velocity that we're pulling with. So that's going to be V. So what we end up with is that the rate of change of flux is magnetic field B times L times V, which means that the current is electromotive force over resistance, so BLV over R. And I want you to notice that the current is proportional to velocity. So the faster you pull this thing, the more current you're going to get. Now we can plug in some simple numbers here: a magnetic field of 1 Tesla, a length of 10 centimeters, so 0.1 meters, speed of 1 meter per second, that's not very fast, and a resistance of 100 ohms, and what we would get is a current of 1 milliampere. Let's look at problem number 14 in the back of the chapter. Problem number 14 says, a circular wire loop 40 centimeters in diameter has resistance 100 ohms and lies in a horizontal plane. A uniform magnetic field points vertically downward, and in 25 milliseconds it increases linearly from 5 to 55 milliteslas. Find the magnetic flux through the loop at A, the beginning, and B, the end of the 25 millisecond period. What is the loop current during this time, and which way does the current flow? All right, here's the setup. I've drawn the picture. There's our magnetic field going from 5 to 55 millitesla, and the time it takes is 25 milliseconds. We can look at the original flux, and remember, flux is going to be B times A times cosine theta, but once again, cosine theta is just 1, so it's BA. And we've got the initial magnetic field times pi r squared. So there I've plugged in the values, 5 times 10 to the negative 3 Tesla times pi times 0.2 meters squared, and we get 6.28 times 10 to the negative 4 Webers. At the end of the 25 milliseconds, the magnetic flux is the new magnetic field times pi r squared. You plug those in, you get 6.91 times 10 to the negative 3 Webers. And finally, the current, the induced current, is going to be the induced electromotive force divided by resistance. That's the change in flux over time divided by resistance, which means we can have in the numerator the change in flux. Well, that's just the difference between these two answers, divided by the time, 25 milliseconds, and the resistance is 100 ohms. So when you plug those in, you get 2.5 milliamperes. The last question, question D, asks, which way does this current flow? And I haven't covered that yet. I will cover that in the next section, but just so you know, it's going to go counterclockwise. And again, we will explore why that is as opposed to clockwise in the next section. And that is the end of sections 1 and 2 of chapter 27. Have a great day.